All right, problem number 31 on page 921. It says one electron collides elastically with a second electron initially at rest. After the collision, the radii of their trajectories are 1 centimeter and 2.4 centimeters. The trajectories are perpendicular to a uniform magnetic field of magnitude 0.0440 teslas. Determine the energy in kilo-electron volts of the incident electron. And so a couple things you need to know here is that the charge on electron is negative 1.6 times 10 to the negative 19 coulombs, and the mass of an electron is 9.11 times 10 to the negative 31 kilograms. Oh, and 1 electron volt. Well, an electron volt is the energy to move an electron or a proton across 1 volt. That's why they call it an electron volt. Well, a volt is a joule per coulomb. And so the energy to do that, well, it's just the charge of an electron times a joule. So 1 electron is equal to 1.6 times 10 to the negative 19 joules. And I don't know if I ever really told you that before, but sorry. Let's zoom out. And it makes sense to use a unit like electron volts with problems like this, because you're dealing with really, really tiny amounts of energy when you're at the atomic level. And so you might as well use a tiny unit of energy. And so they use electron volts for that sort of thing. All right. So here's what we're given. We're also given, we have some kind of an electron, another electron. This, one of them's moving beforehand. They collide elastically, and then they're, afterwards they're moving in circles like this after the collision. So we're given the radii of these. This is 2.40 centimeters, and the radii for this electron is 1.00 centimeters. And we're given that the B field that these guys are in has a strength of 0.0440 teslas. So that's kind of a mess. And we want to find the energy of the initial electron, the incident electron. I don't know why they, just the one before the collision. What was the kinetic energy of the electron that was moving before the collision? So maybe we can call that K initial. And then, so let's solve it. Well, this is a collision, and it says it's an elastic collision. So for elastic collisions, we know that for that collision that kinetic energy is conserved. That's kind of by definition of what an elastic collision is. So we can say that the initial kinetic energy is equal to the final kinetic energy. Well, what is the final kinetic energy? Well, it's these guys. We're going to say that that's equal to the kinetic energy, and we'll call this R1, and then we'll call this R2, so it'll be the kinetic energy of the second electron. And so this is going to be equal to 1/2 the mass of the electron times V1 squared plus 1/2 the mass of an electron times V2 squared. Okay, now so this tells me what to do. I know what the mass of an electron is, but I need to get the velocities of the electrons. Well, I look at them and they're moving in circles, and after the collision. So if they're moving in circles, then they must be a centripetal force on them. So that's going to be mv squared over r. And but it's a magnetic force that's making them move in a circle. So that can be equal to QV times B. So the centripetal force is equal to the magnetic force. For a freely moving charged particle in a uniform magnetic field and moving in circles, that's what you get. And everything's perpendicular here. You don't have to worry about the cross product between V cross B or any of that. So this lets me solve for V. So that cancels that. Multiplied by R, divide by M. So I can say that V is equal to QB R over M. And so V squared is just going to be this squared. So let's plug that in now. So the initial kinetic energy will be equal to 1/2 the mass. And I'm just going to factor the 1/2 the mass out. So that's going to be V1 squared, which is QBR1 over the mass squared, plus QBR2 over the mass squared. Now this looks kind of messy, so let's just factor out everything so that when I do plug in values it's not quite so cumbersome. So we've got a mass squared here, and that's going to cancel with the mass up here. So we're going to have a 1/2 the mass, and then we've got a Q squared and a B squared. And then what's left is the R1 squared plus the R2 squared. So I think we're ready to plug in our values now. Well, this is equal to 1.6 times 10 to the negative 19 coulombs squared. This is 0.0440 Teslas squared, divided by twice the mass of an electron is 9.11 times 10 to the negative 31 kilograms. Multiply that by R1, but you know, hey, it's 0.0100 meters. You got to change it to meters. Square that, plus R2 is 0.0240 meters squared. And now it's just a big calculator problem. But I did it in advance, and I got 1.84 times 10 to the negative 14 joules. Now that's our answer in joules, and frankly that's, I don't know, that's good enough for me. But it wanted it in electron volts. So let's just say that 1 electron volt, oh, they wanted it in kilo electron volts. Okay, so 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. And so you take that and then you, oh, well, let's do one more. Sorry, hold on. And 1 kilo electron volt is equal to 1,000 electron volts. So I guess that would be like 10 to the negative 16 here if you want to, when you put it in your calculator. And you get 115. And that's my answer. Now, where are the big ideas in this problem? I mean, all this is just calculator work, but the big idea is this. If you have an elastic collision, the initial kinetic energy is equal to the final kinetic energy. You have to remember that. Then you got free moving charged particles in an electric field. They're going to move in circles. And so you can relate the centripetal force to the magnetic force, and you'll get this equation for the velocity. And then you just use that velocity for the two different charges with kinetic energy. And then you hopefully have excellent calculator skills after that. And also, an electron volt is a unit of energy. It's the amount of energy it takes to move the elementary charge, the charge on a proton or an electron, through 1 joule per coulomb. And so you get this conversion factor right here. For 1 electron volt is 1.6 times 10 to the negative 19 joules. Any questions? Let's zoom all the way out. See the whole thing. Okay, that is all.